Thank you very much for the invitation. I am Horacio Saggion from Universitat Pompeu Fabra. I belong to the Natural Language Processing Group. So the talk will be about mining and enriching scientific text collections. But first, I would like to do a little bit of publicity about where we are, where we come from, and the type of research that we carry out. I am at Universitat Pompeu Fabra. It is a public university in Spain. It's quite a young university, and it's named after this person who was Pompeu Fabra, a grammarian and engineer who developed the grammar of the Catalan language. It is, even if it is a young university, it's highly ranked in several international rankings, so very much concentrated on research quality, and we are located in 3 different campuses in the city of Barcelona, and that's the campus where we are located. I am in the Department of Information and Communication Technology. That also is a very young department, and we are located in a district of Barcelona that is called 22 Arroba. It's a technological district of the city where there are many spin-offs and technological companies. We have 5 degrees. One is computer science, other is telecommunication, audiovisual systems, biomedical engineering, and recently we opened a degree on data science. Also relevant for the talk that I'm going to give, we recently received an award from the central government to investigate data-driven knowledge extraction techniques. So what I'm going to talk today has a lot to do with this type of line of research. The Natural Language Processing Group, where we work, it's called TALN, that means Natural Language Processing in Catalan. Started in 2005, founded by Professor Leo Banner, with 4 people, and now has grown to 25 people. So it's a medium NLP group, but for its age, it's quite an impressive achievement to have this number of people. We divide our group in 3 research areas. One is natural language interaction that involves multimedia, multilingual natural language generation, and dialogue systems. So this is head by Leo Banner. Expressive speech synthesis, head by Mireia Farrús, and my laboratory that is the largest scale text understanding systems. And the topics that we address are text simplification, text summarization, information extraction, analysis of social media texts, and dialogue systems. And the funding, so we are few permanent people, and the funding for the researchers that come to work with us and for the students come from different sources, like European research funding and also national funding. Okay, so a little bit about the research that we carry out in my subgroup. So I established a line of research that is automatic text simplification. So in 2010, we started with a project on text simplification of a Spanish language. We developed the first text simplification system for Spanish that tries to address the complexity of the syntax of the sentences and the complexity of the vocabulary. And we also developed the first Spanish text simplification corpus for research. And we developed several applications that perform simplification, and one of them is that web portal that is no longer available in that look, but still we have a demo of the project where you could enter a text and then ask the simplification, and you will get a kind of simplified text. The continuation of that project was an European project where we developed technology, this time for English, following the same techniques and the method that we developed for Spanish. The idea of this project was to integrate people with intellectual disability into the digital world, and especially into social networks, email, and any tool that could help them be integrated in the society. One of the key technological developments was an email client that is called Columba that incorporates, for example, simplification technology for people with intellectual disabilities. Another line of research, this is being done by my PhD student Francesco Barbieri, is detection of figurative language in social media. So we are very much interested in identifying irony, humor, sarcasm, satire in social media. And we develop methods that are based on characteristics of words in order to detect something that is unexpected. So if you have these two tweets, you would like, for example, to say, okay, the first tweet is a real tweet or a normal tweet, and the second tweet is a tweet that has some kind of irony, because you see some unexpected terms there. Also, Francesco recently got interested in analyzing the semantics of emojis. As you analyze the semantics of words, he's interested in analyzing the semantics of emojis to know which emojis can be used in similar contexts, which emojis share the same properties across languages and cultures. And in order to do that, he uses continuous word vector representations. Another line of research is try to create knowledge from raw text. So this has been done by Luis Espinosa, who recently graduated. He got his PhD in July. So he was working on taxonomy construction, automatic taxonomy construction out of data, out of terminology, and also out of definitional statements. So he uses several techniques, supervised techniques, and also word vectors in order to assess the value of the taxonomy that he's creating. Okay, so and the other line of research that we are concentrated on is scientific text mining. So this is the topic of the talk today. And I was involved in scientific summarization years ago, and I had the opportunity to go back to the analysis of scientific text with a project that was called Dr. Inventor that recently finished. It was a project funded by the European Commission in the area of scientific creativity. And the idea of this project, it was a collaborative project. We were partners in this project, providing natural language processing support. The idea of this project was to create an assistant, a virtual assistant, which will go to huge text collections of documents and will try to find analogies between otherwise unrelated documents. Will present visualizations of the information, the analogies found in these documents, and by doing that, the scientists will get inspiration for investigating new things. Okay, so that was the idea. And our job in this project as partners was to provide natural language processing for scientific publications. And obviously, as one of the problems that we face when dealing with scientific publications was that most of the publications are in PDF formats. This is obviously a technological problem. It's not so much a scientific problem, but we have to deal with it. But what was more interesting for us was try to extract from the content of the document useful information. So, for example, to try to identify the pattern of argumentation in scientific documents. So where is the challenge that is being faced by the author? Which is the solution that the author proposes? Which are the advantages or disadvantages of the proposed solutions? We were also interested in not the paper in isolation, but also the paper in the relationship with the other papers that have been published in terms of the citation network, for example. We were interested in knowing the citations that were made by a paper, so why they were made, whether they made to criticize the work, whether they made because you are going to base your work in previous work, and so on. And also interested for us was try to extract the main ideas from the research papers, not only what the author thinks that the main ideas are, but what other information that you could find in the body of the document. Okay, so the first thing that we did is to create a corpus for the analysis that will support our analysis, and this corpus is a corpus of 40 documents in computer graphics, because that was the field that we address in this research. And we decided to collaboratively annotate this corpus for types of information that were interesting for us in order to support the development of our tool. So we developed an annotation tool that is called Annot, that you can do annotation over the web. So there are many tools that exist, but we have our own. And we have annotators that were computational linguists on the one side, and also computer graphic experts. So what we were looking in the documents was rhetorical information. For example, we were interested in knowing for each sentence in the document whether they represent a particular rhetorical move. So we investigated several annotation schemas that exist in the literature. For example, the annotation zoning scheme from Teufel, or the core concepts from Liakata. So we designed our annotation schema looking at previous literature. We tried several annotation schemas that existed, and then we have to come up with a concise set of categories because otherwise annotation will not be reliable. So those are the categories that we wanted to annotate. So the challenge that the author faces, the background information that he is using, the approach that he takes, the results of the investigation, and what he's going to do afterwards. And we have for each sentence in this corpus of 40 documents, 3 annotators, experts in computational linguistics. The second type of information we were interested in was the citation information. So there are also several schemas to annotate citation information, and we basically decided to base our work on the work that has been done at University of Michigan in Radev's team. So we decided to use these 5 categories. So you criticize a work done by a researcher, or you compare your work with another work of another researcher, or you use previous work in order to create your own research, or you use some tools or data or algorithms from other paper in order to do your investigation, or you cite because none of the other categories apply. Okay, so, and in this case we use computer graphic experts to annotate. And finally, because we were interested in the essential content of the documents, what we did is to annotate the sentences for relevance. So we were interested in knowing whether a sentence in the document was completely relevant to be included in a summary, or was absolutely relevant to be included in the summary. And here again we have 3 annotators per document, annotators from computer graphics, and they have to provide numbers for each of the sentences. When we had all this corpus annotated, we created a gold standard version with partially, in some cases, with partially agreed information.
So why only 40 documents? Why not 4,000?
Because we have a limited time, and we need to have the corpus ready for trying to develop the tool. So obviously, the more we have, the better it would have been, but the task of annotating is very, very intensive.
Let me rephrase. How
Yeah.
much time and cost would it require us to go from 40 to 4,000?
Well, this task took us 18 months, not full time, but 18 months. A full researcher working, the person that was dealing with annotation was a part-time person that was working for 18 months. So the expert in annotation guidelines, and training the annotators. Then we had another person that was a full-time person working on the annotation tool and providing all the technical support. And then we have to hire some annotators to deal with the first part. And then we were lucky because we had the collaboration of the partner projects in order to annotate the part of the corpus, but it's an intensive task. Yeah.
So you annotate every single sentence in the paper?
Yeah, every single sentence. Yeah.
And there are a lot of sentences with
Sorry?
a score of 1. The relative
Yeah.
1 to 5. So actually, there are a lot of sentences that get labeled 1.
Yes, exactly. Yes. Yeah. Many. Yes. Sorry.
So what was your inter-annotator agreement
For rhetorical information, it was around 66. Yeah. For summarization, we didn't care much about annotation agreement because summarization is a very subjective task, and we have three scores per sentence, so that we can aggregate them. And I think that for citations, a very small proportion had full agreement. I don't remember the numbers, but I have them later on. I can share them with you. But we had let's say that 80% of the sentences got at least partial agreement. That means two annotators agreeing in one category. Okay, but the 20% we could not have gold standard annotation. Yeah.
What became the gold standard? Was it an aggregate, average, or?
So the gold standard for summaries is absolutely all the information, so that you can then aggregate as you wish. The gold standard for rhetorical information is majority. For citation is majority agreement. So sentences that don't get agreement with two people, we discard them. Yeah. And for rhetorical information, one of the annotators was the one that decided finally the annotation. Okay, it was considered the expert annotator. Okay. Yes.
Small question on the citation annotation. Were
Yeah.
they allowed to mark a citation as both like multiple categories, like it's the criticism and the compare?
Yeah, we had an schema first. We had an schema that had two labels, so one main category and one subcategory. So they were able to annotate those, but I mean it was extremely difficult to get agreement. Okay, okay, I will continue. Okay, so this is a summary of the annotation schema that we have. Yeah, so and we had also we try to have papers from different subfields of computer graphics. The papers, the selection of the papers and the topics were decided by the computer graphic experts, not by us. So they were the ones doing the selection of the documents because we had no expertise in that field. Okay. Okay. So not only based on this corpus, but based also on what was needed for processing the documents, we developed a full tool for the deep analysis of deep. In quotes of scientific papers. Also, there are many steps in this tool. Some steps are not indicated here, but anyways, in one of the main or one of the technical issues that we have to face is to transform the PDF documents into text and into XML representation. So we investigated several tools that were available. So we tried them in a sample of documents from the domain, and we detected good performance and bad performance in some of them. The best one for us was at the time of when we did this was PDFX. That is a tool that is hosted by the University of Manchester. They provide a service where you can send your document and you will get back an XML annotation. So that was the best option for us. And this tool allows us to obtain metadata from the documents and also to extract the structure of the structure in terms of sections, and very important, the bibliography and each of the bibliography entries. So that was very important for us. Then, because we had to process massive amounts of data, at some point the servers at Manchester were down. So and we had to do our experiments. So, so we needed an additional solution. So we, at that time, Grobit started to be available. So we decided to incorporate Grobit in the library. So we have these two options, and now we have our own tool to do PDF to text conversion. Okay. So the second step was to perform word and sentence identification. So the whole architecture that we have, or the whole system, is based on GATE. So we rely on GATE for document annotation, document storage, and all our architecture. So the components are kind of GATE components. So we have follow the architectural precepts of GATE. So we have setters, getters, initializers, and runners. Okay. So we tried with the GATE sentence splitter and word identification. Obviously, the scientific document has a specific characteristics, so we have to change or adapt the splitter and the word, the tokenizer to the particular characteristics of our text. So that was not too complicated. Then we identify what are called inline citations, so the reference that you make in the body of your paper. So this is basically a rule-based approach that we have implemented, plus a voting mechanism. So we have several styles of citation that we run over the document, and then with the voting mechanism, we decide which one is the actual style that is being used, and then we annotate the document with this the winner of the pattern that wins in this case. And then what we do is to, using some heuristics, we link the inline citation with the entry in the bibliography of the paper. Okay, using, for example, year, names of authors, or the number that is being made in the citation. Then instead of parsing the references, what we do is to call several services that provide useful metadata for bibliography. So we use, for example, the REST API from Biblisonomy to get metadata. So the authors, the title of the paper, the conference where the paper was published, and the year, and we enrich with that information our documents. And sometimes we combine information from several sources, but we trust more Biblisonomy. Yes?
What is the coverage of these services?
Sorry?
What is the coverage like for these services that provide additional citation?
I don't know how many papers they cover, but it's quite good. I mean, we tested in our corpus, and it's in our corpus, and also in the collections of documents that we have processed, and it is performing quite good. I cannot tell you a number of how many, what is the precision or recall that we have, but it was performing quite well. Sorry?
Is it a particular domain, or is it general?
No, it's general. Yeah. In Biblisonomy, you can have everything. Yeah. Okay, then we perform a dependency parsing. We use an available parser that was developed by Bernd Bonnet, who was collaborator in our laboratory, and at the time was a quite good parser, and also parser that can be retrained if needed. And the only modification that we did is that we consider citations as well in the sentence. So if a citation has a syntactic role, we pass it to the parser. Otherwise, we don't pass it to the parsers. Yeah? And in order to do that, we use a set of simple rules in order to detect whether the citation has a syntactic role. We also implemented a system for coreference resolution based on the algorithm, the Stanford coreference resolution system. We only, for this tool, we only wanted to have a pronominal coreference, because it's quite, because you will see that what we needed to extract from the documents, we perform open information extraction later on, and some of the triples that we extracted finally contain pronouns that you could not match to anything if you want to compare two different papers. So we needed this coreference resolutor in order to identify the antecedent of pronouns in order to get more compact semantic representations. Okay? And from the Stanford resolution system, we implemented only 4 of the filters that they have implemented until the pronominal coreference. Then we have a process of causality identification. So causality is quite important in discourse and also in particular in scientific text. So because it provides you the reasons why some conclusion has been reached, for example, or some arguments that you can understand the results of an investigation and so on. So we try to identify in sentences and also across sentences causality information, so the cause and the effect. And in order to do that, we have a rule-based system developed by a linguist. So we also try to identify in the sentences clauses, not the whole sentence, that contains the cause and the effect. This is also rule-based, navigating the dependency parse tree. And for identification of the relationship between cause and effect, we use a dictionary of linguistic expressions, cue phrases in particular, and also verbs and nouns that entail causality. The performance of this system in terms of precision is around 75. With lenient, so if we don't consider perfect matching of the elements of the relationship, we can get to 90. But the recall of the system is very low. We have not measured it because we don't have a full corpus annotated with all causality, no causality, and so on. So we cannot measure it. But you can see that in the papers when they come up, there are very few causal sentences. Okay, now for rhetorical annotation. So the objective here is to go to each sentence in the paper and identify one of the five main categories in our annotation schema, such as a challenge or the outcome of the investigation. And in order to do that, what we do is a trainable system. So we take the corpus that we have. So this is our gold standard that we can use for training. We design a set of features based on many characteristics from previous work on rhetorical identification, plus features that we can compute thanks to the previous tools. And we have tried several machine learning algorithms. The one that gave us the best result was the support vector machines, and we get up to 76 FS score on identification of rhetorical categories. Yes?
The input for this problem, what's really is the payroll sentences?
No, for this problem is each sentence annotated with hundreds of features. I will say thousands because we also consider n-grams and bigrams and skipgrams. So several features that have to deal with the position of the sentence in a particular place in the document, where similarity with the title, with particular vocabulary from a dictionary that we have. Yeah, so different features plus n-grams and
dependency information across.
Dependency information as well. Not across different sentences, within the same sentence. Yeah, so we don't look at the relationship between different sentences. It's the sentence as it is. Okay. And for citation purpose identification, we follow a similar approach, but we increase the number of features because here you have to, in citation characterization, you have also to look at lexicons of subjectivity in order to know whether something is criticizing or something is neutral, yeah, something is positive or something is negative. So we have incorporated a number of lexicons to device features. So again, here we try different supervised machine learning systems using the corpus, and here we have kind of disappointing results. We cannot get over 0.40 in FS score. So it is very low. It is a much more complicated problem, but also we have less data, much less data. Yeah, so where we can train our system. And finally, we perform a kind of open information extraction approach where we go to the output from the dependency parser plus the coreference information plus the causality information that we have identified, and we extract triples, subject, verb, object from the representation, and we combine nodes into this representation when they have some coreference links. Okay, so that the final representation will be more compact. I am not saying it here, but we also have one process that performs word sentences abbreviation using an available tool that is Babelfy. So we link words and phrases from the document to BabelNet and perform some kind of word disambiguation. Okay. Well, and finally, we do perform summarization. using an available library that we have, and we train a system for summarization also using the corpus. So basically what we do is to take the information that has been given by the annotators, we aggregate the scores for each sentence, and then each sentence gets a score, and we try to have a system that predicts that particular score. So we design a set of features that have to do with the position of the sentence in the document, whether the sentence contains a specific vocabulary, whether there are citations in the sentence, whether the sentence contains a specific rhetorical category as detected by our system. We also use centrality information provided by text rank or centroid, and all these are numerical features. And based on that, we train a linear regression system. So we learn the weights of each feature, and then we can, with these weights and features, we can score unseen sentences in new documents. And then we rank the sentences, and we extract the top ranked ones for the summary. And has given us good results in several tasks. Okay, so with this library, so we can.
Sorry, can I ask a question
yes.
about the summarization? So
Yeah.
how does your notion of summary of a paper, how does it compare with the abstract for the paper?
How we compare? Well, we haven't evaluated the output against the abstract. We use the abstract as well as one of as the input, so we can select sentences from the abstract itself. So I think that an abstract of a paper, I mean, the vision of the author is completely different from, well, can be different from the vision of someone who is reading the paper. So in the abstract, you will not, for example, put explicit results. You could say in the abstract of in your abstract that you have improved such and such, but you don't say exactly how you have improved, or you don't have the description, the exact description of the methods that you have used that are in the body of the document. So it can be very different from the automatic summaries from the body of the document can be different from those that are in the author abstract.
So the summaries tend to be longer or shorter? It sounds like they will be longer if they include some more of those details.
Well, I mean, this is a parameter of the system, so you can extract so many. So basically, the system ranks the sentences, so you can extract as many sentences as you want for your summary. So it's up to you to decide which sentence, how many sentences you are going to present. We haven't done, so when we compare and we see, when we do the evaluation, what we do is to compare with in addition, I forgot to say that in addition to these numbers, what we have also is for each document 3 manually written summaries from the expert. So the expert goes to the document, reads the sentences, also looks at the numbers that he has put, and writes a summary. Yeah, and we have asked them to write summaries of 250 words. So this is the ones we compare to, not to the abstract of the author. But that's also a valid evaluation to compare to the author abstract.
And when you compare it to the expert summaries, so how do you decide which one is better? How do you measure? What's the metric that you're using?
We use Rouge. That is the established metric for when you have ideal summaries. It would be better to use human assessment, like I read the summary and yeah, this is good. It answers my questions. It tells me everything that I wanted to, but I mean, we have limitations. You know, it's more intensive to do that kind of evaluation.
I have a follow-up question. Qualitatively, what are we hoping to get? Do you feel like the users actually need a better summary than the abstract? Because my feeling is that our users, it's hard to come up with a better summary than in the abstract.
Mm-hmm. Well, it depends. It depends on what your user wants. So, because there are different types of summaries. A summary can be indicative of the content. So, you know, okay, there is a new paper that is in text summarization and word embeddings. Okay, great, I will read it. Or you want to know the techniques that have been used. Oh, this guy is not telling me the techniques that the exact techniques that he's using. I need to go to the document and read it. So it depends. So if you want a summary that will contain the essential information, you forget about the document and you are okay with the summary. Yeah, it's different from the other situation where you need the summary in order to decide whether I will read or not the paper. So it depends. There are different types of summaries. So summaries you could think of situations where you have a question or a set of questions that you want to ask that paper, and the summary answers your questions. So you're okay with that. So it depends, yeah?
But in that sense, the summarization problem is indefined, or it's actually a personalization kind of scenario where what is a good summary really depends on the user.
Yeah, exactly.
So then the annotation doesn't have that.
No, the annotation you have to tell them. You have to give them instructions of what type of summaries you are looking for. For example, in our case is, please extract from this text or write the essential information from this document. So, yeah, obviously there will be subjectivity, because what you consider that is relevant, yeah, for example, might be not relevant for another, because you already have certain knowledge of the task. So some things will be obvious for you and not obvious for another reader. So there is still subjectivity there, but you give some instructions to the people that write the summary. So it's complicated. Okay, so all the work that we did, it was based on this computer graphics scenario of scientific papers, but we have also taken the ACL ontology and processed all the documents and come up with visualizations, HTML visualizations of what the tool is able to do. So this is a short video about the visualization of one paper from ACL. So the system is able to correctly identify, for example, the different sections. You can see that the citations have been correctly spotted, I hope. That the citations have been enriched with the metadata. Then you can go in this visualization to the rhetorical information that has been identified, for example, which is the challenge in this paper. The challenge is that traditional approaches lack generalization, take a lot of human effort, and so on. So that's a particular challenge that probably this author is trying to address. Then you can look at some summary sentences. This is a very simplistic method of performing summarization, but it was able to pick in this particular document sentences that contain the challenge, the background, the challenge, and the techniques that the paper is using. Then you can go to the citations that this paper is making and see the distribution of papers per year, looking at the type of terms that the citations are using, and also look the sentences in the citation in context. And then we have the knowledge representation. It's the kind of knowledge representation that we create, that are the triples connected by coreference relationships. So like the paper proposed a method that aims to extract features. I mean, not very informative, but it's what we get. Or that the authors introduce a model, and also the authors propose some neural network to address some problem, and so on. Yes?
So is this all from the same paper?
This is from the same paper, yes.
Visualization. So how do you deal with duplicate sentences or repetitive sentences where the author maybe at the top says a sentence in the abstract and then more below?
Mm-hmm.
And repetitive in the thing. It seems to me if you have a summary, you just have a lot of repeating sentences.
Mm-hmm.
That maybe one of them is the key and not all.
Yeah, I think you are right. In the case of single document summarization, in general, we assume that there is no repetition, but you are absolutely right, because if you have the abstract, probably there will be something in the body of the document that will contain the same information, maybe a little bit more detail, maybe not. So you're right in that. We don't have a filtering step here. We do it when we have multi-document summarization, but I think it would be useful to have also for single document summarization. Yeah, you're absolutely right. Okay, but these graphs that we have are the graphs that then can be used to do comparison across papers, so you can try to identify analogies across papers. Okay, so this library is available. We don't expose the source code. It is a library. We expose an API to use it, and obviously integrate some services that have to be called in order to get the whole functionalities. Okay, so because we process the whole ACL, and I mean, we have this tool, and there are many data sets that are interesting to investigate, so we decided that we wanted, in the context of this project on intensive data, creating knowledge from data, so we decided that we wanted to analyze online scientific publications, crawl full sites that contain open access publications, for example, store them in our servers, then pass them through our library, and then perform indexing, perform some kind of analysis, and offer visualizations to scientists in order to explore document collections, to explore individual documents. So what we did is to start with a case study with the ACL ontology. So what we did is to combine the output from our system with the Microsoft Academic Graph, the metadata that Microsoft Academic Graph give us on papers. So we started to play with some visualizations using Elasticsearch and Kibana that allow us to create nice visualizations. So you could get the whole ACL universe and see where the papers come from, who are the authors of the papers, who the papers collaborate with. So here you can concentrate on a particular author, see with whom he has been collaborated, and where these authors are located in the map. Okay, so you can go to the whole ACL universe, all the conferences under the umbrella of ACL, and see what is this conference about, what they deal with, or the evolution of number of papers that have been published in the different conferences, and where people in the world send papers to this conference. Also, you can analyze the distribution of papers per different topics. So here you can see information extraction that had a boost here in 2000, for example. You can see that machine learning was not present until the 95, for example, in NLP. Yeah, interesting patterns that you know that are there, but you can see them very clearly here. And you can go to a single conference to see whether there are differences between ACL and empirical methods, for example. Yeah. And you can see the evolution of recent topics, how topics start to get mentioned in conferences in a particular universe. Okay, this is for ACL. So these were just trials of different visualizations, having our tool analyze thousands of documents. And then we decided to go for a small niche study on the analysis of a different collection. It is a collection that comes from the Spanish Society for Natural Language Processing. So it's a society that has over 30 years and publishes a journal, 2 issues of a journal per year. One of the issues of the journal contain the papers that are published in the annual conference of the CPLN, and the other issue is a regular issue. Okay, and all the papers are available. Why this is interesting? First is our society, so Society for NLP, and second, it is interesting because you have this kind of papers, so in 2 languages. So you have papers, scientific papers in Spanish. By the way, there are many scientific papers in Spanish in Spain and also in South America, so it is interesting to mine this type of scientific knowledge. So you can write your paper in Spanish or in English, but the characteristic is that you have also to provide abstract in English, in Spanish, list of keywords in English, in Spanish, title in English and in Spanish. So it is a nice case also for studying machine translation or studying different characteristics that are relevant for us. Okay, so we started with this collection from 2008 to 2016 because more or less they follow a regular pattern in the style of the PDF style. So we started with this set, and we are expanding now to papers. Now we are going to expand to 8 more years, and then the previous years contain PDFs, but are mainly from images, so it will be very difficult to process them. Yeah, but those from 2001 until 2017 can be processed with our tools. Okay, this is to get an idea of the annotation in Gate of one of those documents. So there is a lot of information, but you see that different parts of the document have been annotated. The abstract in Spanish, the abstract in English. Yeah. So the titles, the list of keywords, the sections, and so on. Okay, and this is the visualization. So now we have not just trial, but we have a system, where we can access the whole collection and provide different faceted search. So and the author can reduce the collection to a set and see what's happening in this sub set of the collection, and you can go to individual documents. Okay, so what we did is to start with DBLP that contains most of the entries, most of the bibliographic information about the papers published in the CPLN, and also pointers to the actual PDF. So we collected all that information, so the bib text plus the PDF. And we develop now our own PDF extractor that we call PDF Digest. That the characteristic it has is that it preserves the layout of the PDF paper in order to support better visualizations of individual papers. So we get with the tool the HTML, but plus a style sheet information. And with that information, we have a set of rules that are applied in order to extract the XML that will contain the abstract, the title, the keywords, and all the sections. Okay. Then we have adapted our tool, the pipeline that I already presented. So this tool will be is now able to deal with Spanish and with English. So the system that performs the transformation also detects in each element whether it is written in English or in Spanish. So we use a bi-level library to perform language identification. So we apply one system or another to the different parts. We have not yet implemented all the modules for Spanish. For example, we don't have rhetorical classification in Spanish. We don't have citation purpose identification in Spanish. We have the basic things, like the parsing. We have incorporated the parsing in Spanish. That is the same parser than for English, but trained in Spanish data. When we have the information in XML format, we also perform extract affiliation of authors in order to support visualization in a map of the papers. And we perform also topic analysis in order to support other types of visualization. Then we index the collection with Elasticsearch, and then we provide visualization using Kibana. Okay, so for the transformation of the PDF, so we use PDF to HTML EX to obtain the HTML plus the style sheet information. And then we use a set of rules in order to produce the XML. And we have also a library to validate that the XML is correct. And in the XML, we keep the link between what is in the HTML and we align the information in the XML with the visualization that we will have in the HTML. So in order to not to have not to confuse the user when he wants to see the information in the PDF. And we use this library in order to detect the language in each part of the document. Okay, this is the performance of our new PDF to text extractor system, tested on 30 documents that have been annotated for a number of structural elements. So it's performing quite well, and also is able to deal with other styles like SIGGRAPH or ACL type of paper. Okay, for author affiliation, so we were interested in locating each paper in the map, so we needed to extract the exact location of this institution. Yeah. We also needed to normalize the names of the author to get a unique identifier for each author. So for doing that, it was easy because the BLP, that is where we get information from, already provides a unique identifier for each author, so that's okay. But they don't provide unique identifiers for the location or the affiliation of the author. So we use several tools in order to extract information, DBP, the Spotlight, Babelfy, or a geolocalization application from Google. And also we use the emails of the authors in order to obtain geolocalization information. And this is the performance of the system on a sample of authors from CEPLN. Okay, so we also perform the traditional topic modeling. So, and once we get the topics, we name the topics on the category that we believe they belong to. And then we provide different visualizations. So visualization of papers per distribution of papers per topic, or visualization of papers and collaboration. Yes?
How do you get the topics?
Latent richness allocation.
So
Yeah.
you pick the ones that have the most, have the highest probability?
Yeah, we test with several number of topics, and the one that we saw that 20 was coherent enough, the words that belong to each topic. So we decided to annotate those with these labels. Yeah. So it was trial. So this type of visualization, and then also visualization per topic, so you can get a topic and which papers will be close to that topic. You can go and examine the papers then, and also visualization of authors. And then we have a single document visualization where you can see the paper as if it were a PDF with the information you are interested in terms of rhetorical categories. Here there are not included the summaries, but there should be here another tab for the summaries created automatically. Okay, so if this is working, so this is the actual interface. Okay, so this is the whole universe of the CEPLN. Okay, but you can go, for example, and do some search here. So these are a few papers. So text simplification, you get the few papers that are on text simplification. Let's go to this one that is by Sanya Stachner. So you can look at the paper. So you have the abstract, the summary of the paper. You have the affiliation and everything, and then you have here the paper, and you can go and explore this paper and look for some rhetorical class that you will be interested in. So for example, which is a challenge that Sanya is addressing in this paper. So you can see the main drawbacks of those systems are that such rules cannot be easily adapted, blah, 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 blah. So this is a challenge that she's facing. Okay, and close this. Then you can go and look, for example, at the papers per year, or keywords per year distribution of how many papers per keyword that exists in the in this anthology. Or you can see the topics, the keywords, and you can change and say, okay, now I am interested in sentiment analysis, for example, and it will change. Yeah, so you can see the topics that are being dealt with here, and then you can see a topic graph where you have the topics. You can go to one topic like this one, and then see the papers that are associated to that particular topic, and you can do the same for authors. Okay, so you get the idea. Okay, I think I have to start finishing. Okay, so we are obviously we are all of us overwhelmed by the amount of information that we get on the web, by Twitter and Facebook and every single platform that we use. But also we are overwhelmed by the amount of scientific information available online. So we cannot deal with such amount of information. So the type of tools that I am presenting and also that you work on are very useful for researchers, yeah, and for other types of practitioners. So we have big unstructured data, yeah, so you have, it's basically text that we want to transfer, to translate into some kind of knowledge. So it's not structured knowledge in terms of propositions that then you can reason with, but it's some kind of knowledge. So we hope that we can, with this knowledge support extracted from big structured data, we can provide better and more intelligent search, yeah, for people. That we will be able to provide better answers to people's questions, not just factual. Factual are important. So if I want to know which is the exact parameterization of this algorithm to get this performance, well, I will get the parameterization. That's a fact and will be useful. But maybe speculative questions. What will happen if I apply this method to this problem? And maybe the system is able to give me some information, some argumentation, in order for me to know whether I should go and implement something that will take me maybe 1 month, 2 months, a year. Should I do it or not? Yeah, so some kind of background that can help me decide. If you have all this, we can get better summaries, better state-of-the-art reports. Yeah, we could get the exact information from the documents. Yeah, better maybe the full section of the state-of-the-art that I have to put in my paper. I have my paper written, but I need to write the state-of-the-art report. Can you help me? Yeah. And then for machines, so we expect that machines will be able to perform better recommendations, to draw inferences from this knowledge, yeah, find connections, and propose hypotheses to investigate. So in the future, I am looking to do better visualizations that are targeted to specific users, because I mean, we are our users, but maybe there are specific things that we want to see in a visualization. I think that we need to work towards domain and language adaptation. Yeah, the tools obviously, people in the medical science write different from people in computational linguistics. Yeah, people in engineering write different, so the argumentation is different. So for example, in computer science, you will not find any hypotheses. There are no hypotheses there. Yeah, instead, there are hypotheses in the social sciences. Yeah, so we write different. And if you try to submit a paper to a conference that is not in your domain, it could be rejected because you don't write as they are used to. Yeah? So other types of scientific text, so we would like to explore, for example, tutorials or fora, yeah, or lectures, yeah, so this type of things. And also we need to look more than the text. So we need to look beyond the text. So a scientific paper contains tables, contains images, contains graphics that provide rich information that can complement what is in the text. Also interesting, algorithms, pointers to particular data sets and pointers to the actual software. So all these things are important to also to analyze. And with this, I'll close. So thank you very much. So if you have questions.